A good friend of mine runs a blog on book reviews, which I will link to in the description, and she recently told me that Christopher Paolini, the author of the Eragon series, was about to release his first adult novel. She'd heard that it was a very well-researched sci-fi novel and that the book even includes several papers as appendices justifying the science in the fiction. I did not need any more convincing, so I pre-ordered the book and devoured the almost 900 pages in less than a week, which is really fast for me. I can now falsify that scientific papers are appended at the end, which would probably have led to copyright issues. Rather, Mr. Paolini included a scientific text set in his fictional universe, which included references to real papers. I can verify, however, that the book is very well researched. There is a tremendous amount of references to concepts we know of today. He didn't get them all completely right, but hey, he's an author of fiction after all, not a researcher. I can really appreciate the effort. I therefore feel that it is time for another video about the science of a fictional work. I will go through the topics in order of appearance and will try to keep from spoiling plot elements. This way you can watch the video until you cannot resist the urge to read the book and return once you've done that. There will also be timestamps in the description so that you can skip any parts you're not interested in. I won't be covering the topics as detailed as I would like to, simply because there are so many of them. This is probably going to be my longest video yet and for the near future, so without further ado, let's dive into To Sleep in a Sea of Stars. Part 1, Chapter 3, Section 4, Liquid Gallium and Supercooling. The beacon itself was an amazing artifact. It was, quite simply, a hole. A very large hole. 50 kilometers across and 30 deep, surrounded by a net of liquid gallium that acted as a giant antenna. Gallium is one of the very few elements that is liquid at about room temperature. Its melting point is at 303 Kelvin or 30 degrees Celsius. I don't think the book ever specifies which conditions the Great Beacon is subjected to. I somehow always imagined it in a non-atmospheric environment. This would make sense, because depending on the composition of the atmosphere, it might absorb parts of the electrical signal that the beacon is sending into space. Why then should the gallium be liquid? Well, the melting point of 303 Kelvin is measured at the standard pressure of 1 atmosphere. If the beacon is directly exposed to space, the melting point will be significantly lower. I could not find any data on just how low it would be though. Furthermore, gallium has a tendency to cool below its melting point without becoming a solid, a phenomenon appropriately called supercooling. Many physical calculations assume that a system assumes its ground state, which is the state with lowest energy, and for most substances below their melting point, that ground state is a crystal. However, in reality, it is not always given that this ground state can be reached if the conditions are changed. If you think, for example, of a pencil on a table, then it has a higher energy than if it were lying on the ground, yet it boldly chooses to defy ground state physics and stay aloft. Only if the pencil is disrupted, for example by a strong wind or an accidental elbow, would it assume its ground state. Analogously, the formation of a crystal usually takes some material the crystal can grow on, so if gallium is cooled without the proper environment, it will stay liquid far below its melting point. The electrical resistivity of solid gallium is low enough for it to be used in computers today, and it drops drastically when going to lower temperatures. This is preferable when using it as an antenna because it then loses less energy and does not heat up as much when running electrical currents through it, which is essentially all an antenna is for. I could not find any data on the resistivity of liquid gallium, but if it behaves analogously, cooler temperatures would be beneficial. Why use liquid gallium instead of crystals? I have no clue. Moving on. Part 1, Chapter 3, Section 4, Ternary Code and the Mandelbrot set. For the hole emitted a powerful EMP burst every 5.2 seconds, and with it a blast of structured noise that contained ever-evolving iterations of the Mandelbrot set in ternary code. I am not entirely sure how to understand this sentence, and here's why. EMP stands for electromagnetic pulse, which denotes a short burst of electromagnetic waves. If you have any signal, you can analyze of which frequencies it is made up using a technique called Fourier analysis, which I will not explain here because it is too rich and beautiful to just rush through. Fourier tells us that the shorter the pulse, the more frequencies it contains. In music, you could not assign any note to it, and this is why an EMP can be considered electrical noise. Its acoustic analog is a clap. Hence, I am uncertain if the blast of structured noise means the EMP itself, or if it is an additional phenomenon, possibly even acoustic. The latter would speak against my interpretation that the beacon resides in vacuum. Whatever the case, the noise contains ternary code. We humans tend to use binary code for information processing, meaning that the signal carrier has two significant states. The carrier could be an electromagnetic wave, and the two states could be on and off, or two different frequencies, for example. The two states can encode the digit 0 or 1, and since each number can be expressed in binary representation, and each processable information can be expressed as a number, this allows for communication. The ternary system works completely analogously. Any number can be expressed in base 3, and the three digits 0, 1, and 2 can be encoded in the states off, on, and half intensity, or in three different frequencies, for example. It is possible that our structured noise of the beacon encodes as three digits in three frequencies that are slightly more pronounced, or in three different lengths of the pulse. Now for the really fancy part, the Mandelbrot set. You've probably seen a graphical representation of the set. My aim here is that you understand what the picture stands for. Consider the beautifully simple parametric function fc of z equals z squared plus c for complex numbers c and z. For each value of c, define a series by first plugging in z equals 0, so that fc0 is defined just as c, and then plugging in the last value of the series as the new z. The Mandelbrot set, which is usually shown in black on the pictures, is the set of complex numbers c for which this series is bounded, meaning that the absolute value of fn does not go to infinity if n goes to infinity. The colored part is those numbers that let the series diverge, and the color encodes how fast it diverges. Let's go through some examples. If c equals 0, then any member of the series will be 0, so 0 is in the Mandelbrot set. Take c equals 1. f0 is given by 1. f1 is given by 1 squared plus 1, which is 2. f2 is given by 5. f3 by 26. As you can see, the values become infinitely large as the index goes to infinity. 1 is therefore not in the set. Now consider c equals minus 1. f0 is minus 1. f1 is minus 1 squared minus 1, which is 0. And f2 is minus 1 again. The series is in a loop. It will always oscillate between minus 1 and 0, which means that it is bounded, and hence in the Mandelbrot set. Now take a general complex number c equals a plus ib, and also consider its complex conjugate, c bar equals a minus ib. fc bar 0 is equal to fc0 bar, and it inductively follows that any member of the series for c bar is the complex conjugate of the corresponding member from the series of c. It is thus guaranteed that the Mandelbrot set is symmetric under a mirroring on the real line. Let's go back to the source material. The EMP blast noise contains ever-evolving iterations of the Mandelbrot set. I suppose this means that the builders of the beacon picked a specific value c and now broadcast the values fcn for ever-increasing n. I wonder what c they picked. If it was one of the simple values discussed above, it is unlikely that humankind figured out that they are listening to the Mandelbrot set. But I think, although I am not sure, that there are converging series within the Mandelbrot set that never repeat themselves, which would justify the term ever-evolving. Please correct me if I'm wrong here. Part 1, Chapter 5, Section 5. Bending Lasers. There was a brief flash and a wisp of smoke curled upwards, and then to her astonishment, the laser beam curved around her arm, like water flowing around a stone. What the Xeno was doing wasn't impossible, it was just very difficult. Plenty of materials could bend light. However, to detect the exact wavelength of the laser and then manufacture a coating that could redirect it, and all in a tiny fraction of a second, was no mean feat. Although the speed of light in vacuum is always the same, it changes if the light moves through a material. As a rule of thumb, the speed is lower the denser the material is, which is mathematically represented by a larger refractive index n. If light hits the surface of a medium of different density at an angle theta, then this angle is changed. This is the reason why your arm seems to be at a funny angle if you put it underwater. There are many ways to derive this fact, but I think the simplest one is momentum conservation. A photon has an intrinsic momentum, which is, somewhat counterintuitively, proportional to the inverse of its velocity. If we put our coordinate system such that the tangent of the surface points is the x direction, then the x component of the photon momentum in area 1 is, per trigonometry, equal to the absolute value of the momentum times the sine of theta 1, and the analog is true for area 2. Because of symmetry, the x component of momentum is conserved. The reasons for that are a bit more involved, but I think it is somewhat intuitive if you think about it. Setting p1x equal to p2x and plugging in that the refractive index is defined such that v equals c over n, where c is the speed of light in vacuum, directly gives Snell's law. So yes, it is possible to change the direction light is going in. If you take a material that is not constant in density, you can even make light bend like water. It has to be noted though, that if the laser beam hits the material directly orthogonal to the surface, then there is no bending. This makes sense. How should the symmetric material decide in which direction to bend the laser? In order to avoid the laser beam, the Xeno in the book therefore has to become transparent for the laser of that frequency, adjust its surface such that the beam does not hit it orthogonally, and adjust its density such that the laser curves around Kira's arm. Also, the refracting index is usually color dependent, which is why prisms split white light in the colors of the rainbow, and which is why frequency is mentioned in the passage. And yes, to achieve that in a tiny fraction of a second is certainly no mean feat. Part 1, Chapter 7, Section 1. Apparent gravity through rotation. The apparent gravity lessened as she climbed past deck after deck of the rotating hab section. Gravity is a really strange force. It is really tiny in strength compared with the other fundamental forces, and it is proportional to mass, which also happens to be the quantity that's important for inertial forces. If you are on a spaceship and don't want to miss out on Earth's comforting pull, you have two options we know of. Either take sufficient mass with you, or simulate gravity. Because gravity is such a weak force, you would need enormous amounts of mass on your spaceship, which is really the opposite of what you want. This leaves the weightless astronaut with the inertial forces. Since they are also proportional to mass, they can most aptly simulate the effects of gravity. One could even argue that they are the same, but more on that later. Inertial forces are those that affect a massive body, like yourself, when you are accelerated. You can experience this in everyday life when you are more or less gently pushed in your seat or knocked off your feet, when the tram takes on speed or brakes. So one option to generate artificial gravity is to constantly accelerate your spaceship. This, however, is very energy consuming and of course significantly changes the path you're on. The much more sensible way to achieve this goal is to use the centrifugal force. The principle of the force is the same, the only difference is that the acceleration here is acting perpendicularly to your velocity, while in the example with the tram, it acted parallelly. The centrifugal force is acting on your body because the direction of your velocity is changed, not the absolute value. The result is a circular path. This is realized by rotating parts of spaceships as depicted in many science fiction stories, for example in Stanley Kubrick's 2001 Space Odyssey. The centrifugal force is proportional to the distance r from the center of rotation, so the description that the artificial gravity lessens as Kira gets closer to the ship's inner parts is absolutely correct. Part 1, Chapter 8, Section 1. Newton's third law. The engine looked no different from any of the rockets she was familiar with. Newton's third law didn't care whether you were human or Xeno. Newton's third law states that any force that one body exerts on another produces a counterforce with the same strength and opposite direction. The way almost all our rocket engines work is that they take some propellant, accelerate it to high velocities, and then spit it out in the direction they do not want to go. According to Newton 3, the spaceship pushes itself off the propellant by accelerating it, and thus gains forward momentum. If you want to do calculations on how much speed a rocket of some mass gains by spitting out a droplet of some other mass with a certain velocity, it is in my opinion easier to use momentum conservation, but Newton's third law is what lies at the bottom of it all. Part 1, Chapter 9, Sections 4 and 5. Constant acceleration. Ando kept up the 2G burn for 3 hours, at which point the pseudo-intelligence throttled back the thrust to a more manageable 1.5 Gs, which allowed them to move around the cabin without too much discomfort. The Valkyrie maintained the 1.5 G burn for 16 hours. It is dangerous for authors to give us numbers, so they do it only rarely. Let's take full advantage of this opportunity. 1 G is 9.81 meters per second squared, which is the acceleration with which Earth pulls on you if you stand on its surface. Accelerating with 2G means that the people in the ship feel twice as heavy as they would on Earth, which is certainly not comfortable. The velocity of a body is, per definition, the integral of the acceleration over time, and the covered distance is the integral over the velocity. For constant acceleration, these integrals become fairly standard. The velocity is given by v0 plus a times t minus t0, and the distance is given by d0 plus v0 times t minus t0 plus a half a t minus t0 squared. The velocity of the Valkyrie is close to 0 at the beginning, and she accelerates with 2g for 3 hours. After this time, the ship travels at a velocity of about 212 km per second relative to Adra, which is 0.7 promille of the speed of light. The ship is at a distance of roughly 1.1 million kilometers, which is just under 4 light seconds, or 3 times the distance between the Moon and Earth. The ship then proceeds to accelerate at 1.5 G for another 16 hours, at which point it has reached about 1000 kilometers per second, or 3.5% of the speed of light, and traveled a distance of 37 million kilometers, or a quarter of the distance between the Sun and Earth. It takes light very close to 2 minutes to travel that distance, and since a signal has to travel back and forth for a conversation to happen, there will always be a pause of at least 4 minutes before any question can be answered. A few pages later on, we are told that the light speed gap between the Valkyrie and Adra meant it was over 3 minutes before Chatter's reply arrived. As someone who did the maths, I would have written 4 minutes, not 3, although 4 of course is greater than 3, so the statement is technically correct. I have the theory that Mr. Paolini did the calculation, but during the second acceleration phase forgot the initial velocity of 202 km per second, because then you end up with a total distance very close to 1.5 light minutes. I really like that he did think about this though. If you are wondering if Chatter's reply will be distorted by time dilation, the answer is no. At 3.5% of the speed of light, the time flow is altered by less than a promille. I don't think any human would notice this in a conversation. Part 1, Chapter 9, Section 5. Antimatter as energy storage. As always, the thought of the FTL drive gave her the creeps. Perhaps it was the radioactive death contained in its precious grams of antimatter, and the fact that they could destroy her in an instant if the magnetic bottles failed. Antimatter is the densest way we know to store energy. If matter and antimatter meet, they annihilate each other and convert their complete mass into gamma rays, following the well-known formula of E equals mc squared. Kira thinks about precious grams of antimatter, suggesting that less than a kilogram is stored. If we assume exactly a kilogram of antimatter annihilating another kilogram of normal matter, we get an estimate for the upper limit of the stored energy. It ends up at about 180 quadrillion joules. That does sound like quite a lot, and in fact it is, but remember that the shuttle accelerated to 3.5% of the speed of light already. If we assume that the shuttle with all its inmates weighs 10 tons, which is not much, then its kinetic energy at this velocity is given by 500 quadrillion joules. There either has to be more antimatter on the shuttle, or it is really lightweight. Although I think Mr. Paolini didn't do the maths here, we could put this one on Kira. She's not an astro-engineer, but a xenobiologist. Maybe she just didn't know the correct orders of magnitude. Part 1, Exeunt 1, Section 1. The Planck scale. She'd never observed a Markov bubble in person. The perfection of the mirrored surface fascinated her. It was more than atomically smooth, it was Planck-level smooth. Nothing smoother could exist, as the bubble was made out of the warped surface of space itself. We are now hinging on the border between the world of science and the world of fiction. The Markov bubble is something Mr. Paolini put together from several theoretical papers, as he describes in the fictional article in the appendix of the book. I will not cover the faster-than-light science, because according to our known and tested physics, going faster than light is fundamentally impossible, and because the fictional paper will always do a better job at hinting at the concepts than me. I will, however, take the opportunity to talk about a concept which in my eyes is misunderstood exceedingly often. I've even seen this error happen on a number file video. I am talking about the Planck scale. I've said before that gravity is a strange force, in that it is much weaker than the other forces. To a rather good approximation, the gravitational force and the electric force between two objects can both be described by formulae of the same form. A constant encoding the force's strength times the mass or charge of the objects divided by the distance squared. If you look at the ratio of those forces and plug in the charges and masses for two electrons repelling each other, you find that the gravitational force is weaker by about a factor of 10 to the power of 43. This huge difference is the reason why an oil drop in a relatively weak electric field is massively impacted by the charge of only a single electron. It is only thanks to this that Millikan was able to measure the charge of the electron at the beginning of the 20th century. Now, since finding out that gravity is strange, a lot of time has passed, and humankind has come quite some way in their understanding of physics. Quantum theory has been developed and quantum field theory from it. Two additional fundamental forces have been found, the weak and strong force, and it is now possible to adequately describe those together with the electromagnetic force. Gravity, due to various reasons, still doesn't fit in. For most purposes, this is no problem, because it is so extremely weak that its effect can be neglected in all measurements taking place in the quantum realm. However, if you take two particles and put them at a distance of only 1 Planck length, or have a process that takes only 1 Planck time, it is conjectured that gravity does become relevant even in the quantum realm. This means that the physical theories we know today are insufficient to describe the world at the Planck scale. That's it. I often hear that the Planck length and time are the smallest distance and time interval possible, but there is simply no reason why this should be the case. It is merely true that we cannot yet describe what happens at this scale, but this is not an unusual phenomenon in physics and may well change. Newton's theory of gravity works perfectly fine if you want to describe apples falling from trees or the movement of the moon around the Earth. It utterly fails when describing atomic motion and black hole mergers. For the former phenomenon, quantum dynamics needed to be developed, and general relativity is able to describe the latter. Both are extensions of classical physics in that they predict the same results if you look at the scales classical physics was designed for, but also predict correct results on the more extreme scales. Maybe someday we'll have an extension for describing physics on the Planck scale as well. We are, as of yet, very, very far from measuring anything on that scale though, so it might take some centuries. Part 2, Chapter 2, Section 2. The Equivalence Principle. When troops had boarded the first jelly ship, they had discovered rooms and decks weighted with artificial gravity. And not the spin an object in a large circle kind, but honest to God actual artificial gravity. Physicists weren't surprised. They explained that any species that had figured out how to alter inertial resistance would, by definition, be capable of mimicking a naturally occurring gravitational field. This alludes to the fundamental idea behind general relativity, the equivalence principle. Up until Einstein popularized this idea, the laws of physics knew two kinds of masses, heavy and inertial. Heavy mass takes the role of the charge in Newton's law of gravity, and it is always attracted to other masses. It is the mass that keeps you on Earth's surface. Inertial mass is the proportionality constant in inertial forces. It is responsible for the fact that a boulder is harder to push than a football. You might note that a boulder is also harder to lift than a football. In fact, physicists have tested, and are still testing, if there is any difference in the numerical value of inertial mass and heavy mass. So far, none has been found. Einstein thought this awfully suspicious, so he came up with the equivalence principle and proposed that inertial and heavy mass are fundamentally the same. He then went on, over the course of years, to develop the theory of general relativity, which states that gravity can be described as, and in all sense is, an inertial force. But every other inertial force only ever appears when a body changes its velocity. A little prince standing on the surface of a non-rotating planet keeps his velocity constant, so why doesn't he fly away? The answer that Einstein proposed is that a body not moving through space is still moving through time, and that the fabric of space-time is warped by the presence of masses, leading to an accelerated movement and hence the inertial force of gravity. The warping of space-time is described by the Einstein field equations, which are infamously hard to solve. One amusing side note: the equivalence principle means that any gravitational force can be explained inertially, but it also means the reverse, because any acceleration can always be transformed away. If you are spinning on the spot, you can either describe your arms being pulled outwards because they are on an accelerated path, or because the mass of the entire universe is spinning around you. The mathematics of general relativity does not tell you which interpretation is correct. Coming back to the book, yes, if a species knew how to influence inertial forces, it could most certainly create artificial gravity without accelerating in space. Just accelerate in time. Easy. Part 2, Chapter 2, Section 3. Stardust and Heat Death. Have you ever considered the fact that everything we are originates from the remnants of stars that once exploded? It's a lovely thought, but I don't see the relevance. We, and by extension the universe, will learn to expand beyond this realm and save ourselves from otherwise inevitable extinction, Kira said, by escaping the heat death of this space. There are two concepts mentioned here, and I have to agree with Kira, they don't have anything to do with one another. The first thing is that everything we are made of originates from exploded stars. Shortly after the Big Bang, the universe was mainly filled with electrons and protons in a plasma. It then expanded and cooled down sufficiently for the particles to combine to hydrogen. The universe was dense enough for some of those hydrogen atoms to fuse together to form some helium and very little lithium. Heavier elements did not exist in measurable quantities. The universe kept expanding and was then mainly composed of uniformly distributed hydrogen gas. The gas clouds then began to collapse under their own gravity, becoming denser and denser until the conditions were just right for hydrogen to start fusing to helium again. Those were the first stars. A fusion process creates energy in form of gamma photons, which push against the other atoms and act as a counterforce to gravity. Without these photons, the star would just instantly collapse. At some point, stars run out of hydrogen and start creating heavier elements. However, the energy gained by fusion lessens when going to heavier elements, until it becomes negative when trying to fuse iron with anything else. Some heavier elements can still be created in the last moments of a large star, but not in great quantities. It is not known for sure where the heaviest elements come from. Some time ago I heard a talk about a simulation that managed to explain their creation by two merging neutron stars. These events are rather rare, but one such event some light years away and some billion years ago would, according to the simulation, be sufficient to explain the abundance of heavy elements we see on Earth. Therefore, everything we are probably originated in the Big Bang in case of hydrogen, from stars that exploded in case of the elements from helium to iron, and during a single neutron star merger event in our galactic vicinity in case of the heavier elements. And now for the heat death. I've explained in my video about the physics of tenet that entropy, a measure of the number of microscopic realizations of given macroscopic parameters, always increases in a closed system. As far as we know, the universe is such a closed system. If it keeps expanding, and observations suggest this, then at some point it will have reached a state of extremely high entropy in which all atoms are the same, are evenly distributed and have the same temperature. It is very justified to call humankind extinct at this point. The entropists in To Sleep in a Sea of Stars seek to avert our race's untimely end by learning how to decrease entropy, even in closed systems. I agree that being able to do that would be rather cool, and will have lots of applications besides saving the universe, but I fear that there might be more pressing matters than the heat death. We might reach this state in maybe 10 to the 20 years, that's several billion times the current age of the universe. Part 2, Chapter 9, Section 3, Different Infinities. The entropists came over then, and Vera said, "Our apologies for causing such a disturbance, prisoner. The fault is ours for telling the numinists that there are greater infinities than the set of real numbers. For some reason that offends their concept of the number supreme." This one bugs me the most, because it was so close to being really good before making a crude mistake. So, the numinists are members of a religious society that teaches that there is a superior number. If I remember correctly, it is implied that the first numinist one day started counting, probably at 0 or 1, and the society hopes to reach the number supreme by just counting up to it. They probably have the current number saved somewhere, and their version of a sermon is a priest reading out its digits. I think this is a wonderful and creative mixture of mathematics and religion. Now for infinities. There are infinitely many natural numbers, as you can always just add 1 to any number and get a new one. There are also infinitely many whole numbers, because for any natural number n, you can just take negative n. Ignoring 0 for the moment, this means that there are twice as many whole numbers as there are natural numbers, right? Well, not quite. Infinity breaks things. To prove this, you can start counting the whole numbers in a particular fashion. Start with 0 as the first number, then 1 as the second, but then -1 as the third, 2 as the fourth, -2 as the fifth, and so on. With every step you take in the natural numbers, you jump back and forth between positive and negative in the whole numbers. But, and this is the important point, eventually you will reach every whole number you can think of. This means that there are, in a sense, equally many whole numbers as natural numbers, although this might seem very unintuitive. Mathematicians say that any set in which every element can be labeled with a distinct natural number is countable, and even if it is infinitely large, it is still not larger than the natural numbers. This begs the question, is there a set that is truly larger than the natural numbers? The answer was given in 1891 by Georg Cantor in a beautiful proof. He considered the set of real numbers. Any real number can be written as an infinitely long string of digits. If the digits behind the decimal point would terminate, you can just add infinitely many zeros. Now suppose that we have any numbering of all real numbers. Just for simplicity, I focus on real numbers between 0 and 1 here. We can now artificially construct a new number by taking the first digit of the first number, the second digit of the second number, and so on. We then add 1 to every digit without carrying over decimal jumps. As a number represented by infinitely many digits after the decimal points, r is clearly in the set of real numbers. But is it in our numbering system? It cannot be the first number, because the first decimal digit differs. Analogously, it cannot be the second number, because the second digit is different. You see where this is going. For any natural number n, the nth digit of r differs from the nth digit of the nth number. We can thus conclude that r is not part of our counting system, and that the set of natural numbers, although infinitely large, is smaller than the set of real numbers. And this is what I think Mr. Paolini wanted the entropists to say to the numinist. It would have been one of my favorite passages. Alas, what they did say was that there are greater infinities than the set of real numbers. This statement, while true, makes no sense here. Since the numinists are explicitly said to be counting, it only makes sense for them to live in a countable mindset. The natural numbers are then, well, the most natural choice. Telling them that there are greater infinities than the size of their set would surely upset them, but comparing two sets the numinists don't have anything to do with is a strange move by the entropists, who should know better. Part 2, Chapter 9, Section 4. Space Elevator. The alien ship had succeeded in ramming and severing the ribbon-shaped cable of the space elevator 3/4 of the way to the asteroid that served as a counterweight. As Kira watched, the upper part of the elevator, counterweight included, hurtled away from Ruslan at greater than escape velocity, while the lower section began to curve towards the planet like a giant whip wrapping around a ball. "Phew-ly," Kira murmured. The higher parts of the cable would either break off or burn up in the atmosphere. Farther down, though, close to the ground, the collapse would be devastating. First off, what's a space elevator? Imagine you have a retractable pole and hold it upright while standing at the equator. When you extend it really far, you will notice that it gets lighter. This is because the upper parts of the pole are farther away from Earth's gravity and, much more importantly, because they are on a large circular orbit due to Earth's rotation. It is this increasing centrifugal force that will eventually make the pole fly away, because more parts of it are accelerated away from Earth than towards it. A space elevator is basically just that. A long pole or rope extending outwards into space, held aloft by the centrifugal force due to Earth's rotation. And I mean long. A space elevator on Earth would have to extend at least 35,000 kilometers above the Earth's surface. Using such an elevator would be vastly more energy efficient than using rockets, because you need no propellant whatsoever to get to the top of the elevator, and once you are there you can, in principle, just let go and fall away from Earth. In the text, an asteroid serving as a counterweight is mentioned. This is an idea I've read several times, but it seems a bit odd to me. One option would be to just make the cable long enough so that its own mass acts as a counterweight. This has the additional advantage that the velocity at the end of the elevator is considerably higher. One reason against this is that the cable material needs to be very special. In fact, we do at the moment not know any material that would be suited for a space elevator, so producing it might be exceedingly expensive. When using a counterweight though, anything works. It could be a big ball of lead, atomic waste, or the world's most expensive hotel. I don't see why anyone should go through the complicated process of capturing an asteroid. Okay, after the cable is severed, the upper part flies away at greater than escape velocity. This checks out. Escape velocity is the velocity you need to acquire such that you will fly away from the gravitational potential of a body without needing to add any more energy. Because gravity's pull lessens over distance, your escape velocity depends on your position relative to the body. The upper parts of the elevator are above local escape velocity, otherwise they would not be pulling upwards. The lower parts of the cable are below escape velocity and hence fall down. It is hard to estimate how fast that happens. Even if we knew the mass and length of the cable and mass and rotational period of Ruslan, the mathematics would get a bit more involved, because the cable is an extremely long and probably bendable object that experiences different gravitational pulls at different parts and is moving with an initial velocity perpendicular to the planet's surface. Just to get an idea of the order of magnitude, I will assume that the upper parts of the cable hit Ruslan's atmosphere at roughly the escape velocity from Earth's surface, which is 11 km per second. This is probably too large, but it is noteworthy that most meteors hit Earth at around 30 km per second and are only about as small as a grain of sand. This means that a cable for a space elevator, which is probably made from some very resilient material, would largely survive the fall through the atmosphere and come down as a several thousand kilometers long red-hot glowing string. So I disagree with the part where the cable burns up, but I agree that the crash will be devastating. Part 2, Chapter 11, Section 1. Fission versus Fusion. The missiles would be packed full of fissionable material, and fission scared her nearly as much as antimatter. It was the dirty, nasty form of nuclear energy. Shut down a fusion reactor and the only radioactive materials left were those that had been made radioactive by neutron bombardment. Shut down a fission reactor and you had a deadly, possibly explosive pile of unstable elements with a half-life that meant they would stay hazardous for thousands of years. On the most fundamental level, fission and fusion are based on the same principle. You start with a bunch of atomic nuclei or neutrons and end up with another bunch of nuclei or neutrons. Because of different binding energies, the total mass of the bunch before the reaction is larger than after, and this mass difference is converted to kinetic energy and photons, again according to E = mc². Both processes don't just happen at large scales, otherwise they would long have happened. They have to be started. And here's the difference between the fission and fusion processes we know how to control. Fission is started by taking some heavy atoms like uranium and shooting neutrons at them. Some of them hit the nuclei, which makes them unstable. They then quickly decay, usually transforming to two lighter nuclei and, crucially, several free neutrons. Those neutrons can then hit other uranium nuclei, and thus we have a chain reaction. If left unchecked, this chain reaction goes on until most of the uranium atoms are destroyed. This is an awfully quick process and is exactly what happens in an atomic bomb. In a fission reactor, the process is quenched by adding some other materials to the system that absorb some of the neutrons. This turns a fission reactor into a balancing act. If the process is quenched too much, the reaction just stops. If it is quenched too little, it becomes uncontrollable at some point. The latter is what happened at Chernobyl and Fukushima. It is not yet possible to harness the energy of a fusion reactor. One challenge is that the reaction needs incredibly high pressures and temperatures to start. As far as I know, this is at the moment achieved by making heavy hydrogen float in the middle of a chamber using a magnetic field, and then shooting at it with several lasers to compress it. The lasers need to maintain their pressure for the reaction to continue, meaning that if any part of the system fails, the fusion just stops. This makes it very hard to overall gain any energy, but on the other hand, it is way safer than a fission reactor. The typical initial nuclei in a fusion process are hydrogen, which is just a proton, or deuterium, which is a proton and a neutron. The end results are free neutrons, tritium, which is a proton and two neutrons, helium-3 or helium-4. Of these products, only tritium is radioactive. It decays to helium-3 with a half-life of about 12 years, emitting an electron in the process. It is only produced in small quantities though. The products of fission are more complicated and diverse because there are several candidates as mother nuclei and because they have many more decay channels. Among the common yield of an uranium-235 reaction are cesium-137 and cesium-135, to name only two. Cesium-137 has a half-life comparable to that of tritium, and likewise easily dissolves in water and enters the body, where it decays over the human lifespan. Cesium-135 has the same chemical properties, but has a half-life of 2.3 million years. The other products of fission cover the whole range of half-lives, from milliseconds to millions of years. So Kira is right to be more scared of fission than of fusion. The former reaction leaves the world with loads of nasty products, and the latter is even harder to start accidentally and cannot go out of hand. The energy gain is horrendously high in both cases. Part 2, Chapter 11, Section 6. Blank verse. Heave and bluster, boil and froth, you can't conceal the void within your words. If knowledge were yours, then confidence too, but 'tisn't, so isn't. Cracked the pedestal and perilous the statue that stands above. Gregorovich. Blank verse? Seriously? Is that the best you can do? Kira. Some people seem to think that speaking blank verse means using words that sound like Shakespeare might have used them. Well, no. Blank verse means speaking in a certain rhythm, in which individual lines generally do not rhyme, but yet there are lines. Usually, this rhythm is the iambic pentameter, meaning that 5 pairs of unstressed and stressed syllable make up a line. This is not a strict rule to be followed perfectly, but I don't see it applied anywhere here. Up to the full stop, the given text is a perfect trochee, so this I'll let count as blank verse, if with unusual meter. It then gets more and more irregular. I think the first 3 lines can be saved by adding and subtracting a word here and there. So heave and bluster, boil and froth, you can't conceal the void within your words. If knowledge yours, then confidence too. My poetry skills aren't sufficient to work on the rest. Let's just accept that it is prose. Part 3, Chapter 1, Section 1. Crammed planets. 7 planets nested around the small dim star. 1 gas giant and 6 terrestrial. The rocky planets were crammed in close to the star. The farthest one out orbited at only 0.043 AU. Then there was a gap and a sparse asteroid field, and the gas giant at 0.061 AU. Closer to the star, Bug Hunt, a second, thinner band of debris occupied the space between the second and third planets. Oof, this really pushed my suspension of disbelief. Any system with 3 or more bodies is not intrinsically stable. The solar system is only stable because the planets are so far apart. Still, over these huge distances, they interact enough with one another to affect their respective orbits, which is why many planets have something called an orbital resonance. If you cram planets close together, all kinds of things can happen. If planet E, the one at 0.043 AU, is just behind the gas giant, it feels the gravitational pull not only from the Sun, but also from the giant, which over time might well give it enough momentum to just slingshot it out of the system. Alternatively, it might lose enough momentum to fall into its star. And now the system has 7 planets, all within 0.061 AU, which is about 1/5 of the distance between Mercury and the Sun. Nah, I find it exceedingly hard to believe this. Part 3, Chapter 1, Section 1. Dyson ring. Maybe it was a Dyson ring. I didn't think any material was strong enough to make a ring that big, said Vishal. Huayong shook her head. Does not have to be a solid ring. Could be lots of satellites or stations put all around the star. See? Almost all of the energy on Earth comes in the end from the Sun. This is, however, only a small fraction of what the Sun is giving off, as we receive only that part of the radiation that hits the surface of the Earth. To find the fraction of the total power we receive, we can divide the 2-dimensional surface of the Earth, as seen from the Sun, by the total surface of an imaginary sphere with a radius equal to the distance between Earth and Sun. The result is 4.5 times 10 to the power of minus 10. If we could harvest all energy that the Earth is receiving from the Sun, which, we can't, we still would only use the tiniest fraction of what the Sun is giving off. The physicist Freeman Dyson, who died this year, hypothesized that highly advanced species might harness more of the energy of their star by basically building huge numbers of solar panels in space. One intermediate step is the Dyson ring, in which the solar panels are all in the same orbit around their star, but with a different phase, such that they form a ring around it. I'm a bit puzzled by the remark concerning the material strength. If we have an army of satellites orbiting, then there are next to no forces between them, so you could just connect them to a single solid ring. A complete sphere is a different story entirely, because it can rotate only around one axis, so most of the sphere is pulled inwards by the star's gravity without centrifugal forces to cancel this effect. There is indeed no material known to build such a construct. There is also the concept of a solid ring that rotates faster than orbital velocity. This construct has the advantage that a species could live on its inner surface and experience artificial gravity. This ring would also require a material stronger than any we know. Maybe Vishal got confused, or maybe I'm missing something like orbital distortions or other effects. Part 3, Chapter 1, Section 1. Tidal locking. The planet is tidally locked with Burgund, they all are, but maybe we get lucky with the side facing us. Kepler's law, describing two bodies rotating around a common center of gravity, works very well for point-like bodies. As it happens, planets and moons tend to be three-dimensional objects. The side of the bodies facing the partner is closer to the source of gravity, and thus experiences a slightly stronger pull. The reverse is true for the side not facing the partner. If celestial bodies were perfectly radially symmetric, these contributions would just cancel out and have no effect. Once again, reality is more interesting, so you can usually find one half of a body that is just a bit more massive than the other. The bodies are at a lower potential energy if their heavier side is facing the other body, so over millions of years they tend to adjust their rotational period to their orbital period, such that the heavy side is always facing the other body. The time it takes for this to happen increases drastically if the bodies are far apart. This effect is called tidal locking, and it happened to most moons in our solar system, including our own. Most planets are too heavy compared to their partner to also tidally lock with them, but Mercury is tidally locked with the Sun, and Pluto is tidally locked with its own moon Charon, which I think is adorable. Now we have planets within 0.063 AU around a star. I would definitely expect them to be tidally locked, even if they only orbit a red dwarf. Part 3, Chapter 1, Section 2. Water. Then Kira settled in to study the surface of planet E. There was a lot to study. It was 0.7 the diameter of Earth and nearly the same density. That meant water, and possibly native life. Okay, first off, there is an error on page 490, which displays an image of the system. The radius here is given as 0.35 Earth radii, but if the diameter is 0.7 times the diameter of Earth, then the same is true for the radius. Someone divided by 2 one too many times. 70% of Earth's diameter at the same density means that the mass of the planet, which scales with the radius to the power of 3, is about 34% that of Earth, or 3 times that of Mars. The gravitational pull on the surface is given by Newton's law. Because the mass at constant density scales with the power of 3, and the radius enters with a power of -2, the surface acceleration on planet E is 70% of that on Earth. To conclude that there is water and possibly life is bold. Water is not a rare substance in the universe, and it is brought to the surface of young planets via collisions with asteroids. What happens with the water then depends on much more than the mass of the planet though. If it has no magnetosphere, for example, the solar winds tend to strip it of any atmosphere, and any evaporating water is just pushed off into space. This is what likely happened to Mars. Even an existing magnetosphere might fail to protect the planet if it is too close to the star, as is very much the case with planet E. This fate has befallen Mercury. Then again, the discovery of water in places never expected to contain some has become somewhat common in the past decades. Mars, as it turns out, has a North Pole cap made of water ice and hosts lots of ice underneath its surface. There are even chunks of ice on Mercury, in craters that due to the tidal locking are in eternal shadow. Most of that ice is solid though, so the development of life in it is most unlikely. Part 3, Chapter 1, Section 3. Stationary Orbits. By planet E, a cluster of junked satellites parked in what would have been a geostationary orbit if the planet hadn't been tidally locked. This doesn't make any sense. An orbit is stationary if the orbital period of the satellite is equal to the rotational period of the planet. If the planet is tidally locked with its star, that period is also the local year. In this scenario, the only stationary orbits are the so-called Lagrange points. To tell if the orbit would be stationary if the planet wasn't tidally locked means that Kira somehow had to know the orbital period of the planet at the time the satellite was launched. Even if she could somehow extract it, due to the small distance between the planet and the Sun, I'd expect it to already be tidally locked by the time an intelligent species developed satellites. So either the satellites sit in the Lagrange points and are in a stationary orbit, or they are not. Part 3, Chapter 1, Section 6. Tesla Coils. We put some Tesla coils on stage and used them to play music. Then I rigged up a skin suit to work as a Faraday cage, and I stood between the coils and caught the lightning bolts with my hands, arms, that sort of thing. It was awesome. That's awesome indeed. Tesla coils were invented by Nikola Tesla. They are able to produce very high voltages, so high that the air in the vicinity can be ionized such that small lightnings are produced. This lightning expands the air, giving off a sound, and that sound in turn can be modulated to a frequency. This way, the Tesla coils can be used to produce music. If you've never seen this, search for singing Tesla coils on YouTube. The Faraday cage was in turn invented by Michael Faraday. It is a cage or suit made of a conductive material. If an electric field hits the material, the electrons inside are accelerated and produce the exact opposite field, such that there is no field left inside. This is why a person in a Faraday cage is not affected by the lightnings of a Tesla coil and can safely pretend to catch them. Part 3, Chapter 2, Section 2, Flash Tracing. Flash trace. The concept was pretty simple. If you wanted to see what had happened at a location prior to the time of your arrival, all you had to do was go FTL and fly away from the location until you traveled a distance greater than the light from the event. Then you just parked your ship in open space, turned on your telescope and waited. Not much to add here, the idea is correctly and well explained. Just go faster than light and you see the past. Easy. Part 3, Chapter 3, Section 2. Fractals. The ancient outline of the city was, as she had suspected, a fractal, and the shape of it contained meaning. There, at the nexus of the pattern, where it coiled on itself like a nautilus shell. There, at the center of it all. A fractal is a self-similar structure with a fractal dimension greater than its topological dimension that is nowhere differentiable. Let's break that down. A structure is self-similar if you can find the same structures over and over again if you zoom in. Probably the most famous fractal is the already mentioned Mandelbrot set. You might have seen a video zooming in on the set deeper and deeper, the famous shape appearing over and over again. If not, you should, it's deeply satisfying. But already by looking at the graphical representation you can see the shape appear several times. Infinitely many times in theory. Self-similarity is connected to recursion relations. The Mandelbrot set is also defined by one. It is a common misconception, though, that every recursion relation produces a fractal. This is because of the other conditions, which are much more technical. For many objects, the topological dimension corresponds to what you would expect. A straight line is a one-dimensional object, a circle is two-dimensional, and the circumference of a circle is one-dimensional. It is the minimum number of parameters you need to describe a point on the object. The formal definition of topological dimensionality makes it sometimes cumbersome to see things that seem obvious, but on the other hand it allows you to find out the dimensionality of objects in which the intuition of most people breaks down. This is a very common trade-off in mathematics. The fractional dimensionality is just a different definition for the dimensionality of an object. I haven't shown you either, because they both are deeply nested in measure theory. For the objects mentioned above, the dimensionalities agree. For fractals, this is not true. One easily explained fractal is the Sierpinski carpet. It can be constructed as follows. Start with a square. Divide the square into 9 equal subsquares and remove the middle one. Repeat this recursively for all 8 remaining subsquares. It can be shown that if you repeat this step infinitely many times, the area of the resulting object is 0, and every point in the object has a neighbor that is not within. It is thus somewhat intuitive to say that the once two-dimensional square has become a one-dimensional fractal, and this is indeed its topological dimension. The fractal dimension of the carpet, in contrast, is given by the logarithm of 8 divided by the logarithm of 3, which is about 1.9. As you can see, fractal dimensions do not have to be natural numbers, and the fractal dimension of the Sierpinski carpet is indeed larger than its topological dimension. Then there is the condition that a fractal is non-differentiable, which is a mathematical way of saying that the border is jagged. Any discontinuous function is non-differentiable, but there are also continuous functions that do not have a finite derivative anywhere. One such example is, you guessed it, the border of the Mandelbrot set. A much more graspable example are the Weierstrass functions, one of which is, for example, f of x is the sum of n from 0 to infinity over 1/2 to the power of n times cosine of 17 to the power of n times pi times x. The absolute value of the cosine function is never larger than 1, so the series gives a finite value for every value of x, because the sum over something smaller than 1 to the power of n converges. You could just assume that this is also true for the derivative and just write it down. But now you have 17 over 2 to the power of n as a prefactor, which is much larger than 1. You could hope that the values of the sign make the whole setup sufficiently small, but skipping some details here, it doesn't. The series diverges. This means that you are not allowed to individually derive every term of the sum in the first place. So there you have it, a continuous function that is nowhere differentiable, and, in fact, a fractal. Fractal-like structures are often observed in nature. Famous examples include snowflakes, lightning bolts, ferns, and Romanesco broccoli. Of course, the self-similarity doesn't continue down to infinity here, but stops at some point due to the finite size of cells and, in case of snowflakes, even atoms. The shell of the Nautilus is self-similar, and there are parts of the Mandelbrot set that remind of it, but since the surface of the Nautilus is very smooth, it is not mathematically a fractal. The book didn't say it was, I just wanted to clarify. Part 3, Chapter 5, Section 1. Antimatter Fallout. But the storm had already struck in the form of annihilating antimatter. Kira wondered how well the soft plate would protect her from the fallout. If they actually made it back into space, she'd have to get some radiation pills from the medic. Okay, if you release a bit of antimatter into the much more normal matter of the upper atmosphere, then it is quite likely that some of the resulting nuclei will end up unstable and fall down to Earth. The primary danger of radioactive fallout is that materials can get absorbed by the body after ingestion, where they decay and potentially damage genetic material. Prominent candidates for this are iodine-131 and the already mentioned cesium-137. Radiation pills contain large doses of the non-radioactive isotopes of those atoms, with the idea that your body replaces the radioactive ones before they can decay. Thing is, those are not substances that just float around, they are far too heavy. The panel on page 490 even tells us the composition of the atmosphere, it is fairly Earth-like. If you detonate an antimatter bomb up there, you will end up with atoms with between 1 and maybe 20 nucleons. Sure, if you eat food that contains large amounts of carbon-11, this will get absorbed by your body and decay there, but the variant of a radiation pill suited for this situation is just any food that's not contaminated. A sandwich will do. Also, the fallout should not have reached Kira yet, and she hasn't eaten anything, so she should be absolutely fine in terms of contaminated food. This does not mean Kira hasn't taken any radiation damage. Matter-antimatter annihilation produces gamma rays, and I'm sure some of the resulting decay processes produce energetic beta radiation. Both have a fair chance of reaching her, especially gamma, which is notoriously hard to block. This might have damaged her tissue or her DNA, but no amount of pills is going to fix that. Part 3, Chapter 5, Section 1. Bomb-induced Aurorae. The mushroom cloud had punched a large circular hole in the overcast sky. Through the opening in the tattered billows of mist, Kira saw great sheets of color rippling across the twinkling expanse. Reds and blues and green yellows shifting like ribbons of gossamer silk in a vast neon display thousands of kilometers across. The sight left Kira awestruck. She had only seen the Aurorae a few times on Wayland and never in anything but the darkest night. "What's causing it?" she asked. "Nukes or antimatter in the upper atmosphere, anything that dumps charged particles into the ionosphere." Aurorae on Earth are caused by the solar wind, which is a stream of highly energetic charged particles. The precise process is not yet understood. A nuclear reaction or antimatter bomb is, as discussed, very likely to create unstable nuclei, many of which decay via the beta channel, which releases an electron. Those isotopes that have a half-life on the order of minutes will keep up a significant supply for some time, so a continuous dump of charged particles into the atmosphere is plausible. Still, I do not think that this would cause Aurorae. The solar wind is stopped at Earth's magnetopause, which is typically at a height of round about 50,000 kilometers. The ionosphere, which, by the way, has its name because it is made up of charged particles, is situated at about 100 kilometers above the surface. Dumping more charged particles into the ionosphere is therefore a rather different process and likely has a different effect. Also, releasing a bunch of antimatter that far up would be fairly unspectacular, as there's so little matter that it can annihilate with. If what is described in the passage would work, I would also expect it to work for atomic bombs, and I haven't found any reports about Aurorae during tests. Part 3, Chapter 7, Section 2. Variability of Red Dwarfs. "Grigorovich," said Falcone, "any chance of a solar flare?" Smart. Like all red dwarfs, Buchund would be prone to high variability, which meant enormous and unpredictable solar flares. Red dwarfs are indeed among the most variable stars we know of, and a flare can double its brightness within minutes. I can't add anything here, but just wanted to confirm it. By the way, this makes it even harder for life to develop on planet E. Part 4, Chapter 3, Section 2. The Coriolis effect. At one intersection between the hall and another passageway, she jogged around a fountain where the stream of water traced 2/3 of an infinity symbol as it rose and fell. It was a small thing, but the sight fascinated Kira in an obscure way. The Coriolis effect never failed to mess with her sense of how gravity, or the appearance of gravity, should work. The Coriolis force is an inertial force that arises when you move on a rotating body, besides the much better known centrifugal force. Its formula is given by -2m times the vector product of omega and v, where omega is the vector pointing along the axis of rotation and v is the velocity of the mass m. It has the amusing properties that it only appears if you're moving inside your rotating system, and that it acts perpendicular on your movement. We've covered before that a rotating ring can simulate gravity via the centrifugal force. Well, the Coriolis force somewhat destroys this illusion. If you throw a ball in the air on the surface of a planet, it just comes straight down. If you throw it in a rotating space station, it has a velocity perpendicular to the axis of rotation and thus experiences the Coriolis force, which pushes it off the straight line in the opposite direction to where the station is spinning. For a non-rotating outside observer, this would not seem strange, as the station has rotated away under the ball. The Coriolis force is also well known as the cause for cyclones to rotate in a different direction on the northern than on the southern hemisphere. I think what Mr. Paolini imagined in the passage above was a fountain with two streams of water shooting out into opposite directions orthogonally to the rotational axis. They are then accelerated into different directions such that they curve around, forming something like an S if seen from above. This would indeed be nice to look at. Part 5, Chapter 4, Section 2. Temperature and luminosity of fusion reactors. The fusion reaction was hotter than the surface of any star and brighter too, the brightest flashlight in the galaxy. You might have heard that a fusion reactor works on the same principles as stars, so it might be surprising that a comparably tiny fusion reactor should be hotter and brighter. The reason for this is that fusion in a star only happens because of the tunnel effect. Without it, the pressure, albeit enormous, would not suffice for fusion to happen. This means that the probability of an individual fusion event is much lower than in a fusion reactor. The star is still hot and stable as a whole simply because there are so many hydrogen atoms in total that the overall fusion rate is large. The higher the pressure in the stellar core, the more likely fusion becomes, which is why larger stars, although they have more fuel, live much shorter than smaller stars. So fusion reactors are indeed hotter than the surface or even core of most stars, and they are brighter if you norm the amount of light to the volume. The total luminosity of a reactor is certainly not larger than that of most stars. Our Sun, for example, has a luminosity of about 4 × 10 to the power of 26 watts, meaning that it converts about 4 million tons of mass into electromagnetic energy every second. Your fuel would at least have to have that much mass if it were to keep up this output for 1 second. On a side note, if you look outside our galaxy, the award for the brightest flashlight in the universe goes to quasars, the active centers of some galaxies. A typical quasar converts about 10% of the mass of the Earth to energy every single second. Part 5, Chapter 5, Section 6. Compressed Air Laser Shield. In their hands glimmered light, and in front of them rode a shimmering shockwave of compressed air. Lasers struck the shockwave and she saw how it refracted the blast of energy away. We've covered before that materials with a different local speed of light diffract laser beams at their surface, and that a higher density usually means a lower speed of light and a higher refractive index. Let's assume a spherical symmetry of the shockwave. In that case, once again, if the laser beam hits the surface head-on, which it always does if you aim for the center of the target, it does not get refracted. If you've aimed a bit too much to one side, the higher refractive index of the compressed air will actually correct your error, because the beam will go less off-target inside and resume its original direction inside the sphere. We can conclude that spherical symmetry is not a good idea as a laser shield made of compressed air. If the air in the shockwave was instead decompressed, the effect would be reversed, such that the effective target size would shrink. Let's go for a flat wall instead. Hitting from a position orthogonal to the surface would, once again, just go through unchanged. If the beam hits the surface at an angle, it will come out of the wall as if the shooter had stood at another position. You might think that this makes it harder to aim for the target, but if we assume that the diffractive index does not depend much on the wavelength, then the target appears to you at exactly the position you have to aim at, because its light is affected in the same way yours is. It's a nice idea, but I don't think that it works with compressed air. Part 5, Exeunt 5, Section 2. Solar Sail. She turned, slowly, carefully, ponderously, and the sails caught the light of the sun, and the light reflected with blinding radiance. She could feel the pressure of the photons striking the membrane, urging her onward, away from the sun. The solar wind didn't provide much thrust, but it was some, and Kira felt satisfied that she'd done all she could to quicken her flight. A solar sail is a neat concept. The sun is radiating photons, and every photon has a momentum. It is really not much, but it scales with the surface that is facing the sun. The idea of the solar sail is to make the surface of your spaceship huge without adding significant mass. The material should thus be as light as possible, and it should reflect light, because the change in momentum at absorbing a photon is just equal to the momentum of the photon, while the change is twice as large if the photon is reflected in the direction it came from. According to Wikipedia, an 800 by 800 meter sail at the distance of the Earth from the Sun experiences a force of 5 newtons. If we assume a mass for Kira of 70 kilograms, then she would, under these conditions, experience an acceleration of about 0.07 meters per second squared, or a little less than 1% of Earth's gravitational pull at the surface. Of course, we don't know the exact conditions. This acceleration increases if the sail is larger, the sun is nearer, or Kira is lighter. In any case, the thrust is probably indeed some, but not much. I'd like to point out that the acceleration does not come from the solar wind. A solar sail is powered by the photons radiating from a star. The solar wind is comprised of ionized massive particles. It also contributes to the thrust a tiny bit, but orders of magnitude less than the photon momentum. Wow, this was a long video. If you've honestly seen it whole and not just skipped to the outro, I would be delighted if you'd post a comment with an entry of the Mandelbrot series for c equals 1 plus I over 3, using the value of the last comment of this kind as your zn-1 and starting with z0 equals 0. This will be our secret code. Let's see if we can get to n equals 10. Until then, and also afterwards, have a good time, enjoy science and enjoy fiction.